So leading on from the last video, we can use the idea of oxidation numbers to see whether or not a reaction is a redox reaction and to identify which element has been oxidized and which element has been reduced. Because if the oxidation number increases, the element or the species must have been oxidized. If the oxidation number decreases, then we say the element has been reduced. So if we look at the first example, sodium reacting with hydrochloric acid to make sodium chloride and hydrogen. So the sodium has started life as oxidation number 0, it's ended as +1, so the oxidation number has gone up, so it's been oxidized. The hydrogen has started at +1 and gone to 0, so that oxidation number has been reduced. It's decreased, so we say the hydrogen has been reduced. The chloride has gone from -1 and it stayed at -1, so we call that the spectator ion. We can use the same idea for the next reaction, copper 2 chloride reacting with zinc. Well, copper is starting at the reactant side with the +2 oxidation state, chloride is -1, and the zinc, because it's a metal and it's an element, it has an oxidation number of 0. And on the product side, the copper is now an elemental metal, so it has an oxidation number of 0. The chloride is still -1, and the zinc is now +2. So the species which has had its oxidation number increased is the zinc, so the zinc is being oxidized. The copper is going down in oxidation number, so the copper is being reduced. So the element or the species being reduced is the copper, and the spectator ion is the chloride ion. So the zinc's oxidation number is increased, it's lost 2 electrons, so it's been oxidized, and the copper 2 ions have gained electrons and the oxidation number has decreased, hence it's been reduced. And obviously the spectator ion, as we said, is that chloride ion. For redox, we need to be able to do 2 things. We need to be able to combine 2 half equations to make a total redox equation, but we also need to be able to split a total equation into the 2 half equations. And that's what we're going to do in the next couple of examples. So here is my full reaction. Sodium and hydrochloric acid reacting to form sodium chloride and hydrogen. So underneath I'm going to write the oxidation number of each of the atoms or the ions. So sodium, oxidation number 0 because it's an element. Hydrogen is going to be +1, chloride -1. The sodium chloride, well, the sodium is now an ion, it's +1, the chloride is still -1, and the hydrogen, because it's gone to its elemental form, is now 0. I can rewrite this equation removing the spectator ions, which in this case is the chloride ions, and I get this reaction. I can now split this into the oxidation and the reduction half equations. Well, I know that the sodium is being oxidized because it's going from 0 to +1, and I know the hydrogen is being reduced because it's going from +1 to 0. So I can write my 2 half equations. Our second example was the zinc reacting with copper 2 chloride. So I'm going to write out the full equation. So I have zinc and I have my copper 2 chloride reacting together to form zinc 2 chloride and copper. And again, I'm going to write the oxidation numbers underneath. Well, the zinc, because it's an element, has an oxidation number of 0. Copper, because it's part of your compound, is going to be +2. Chloride, again, -1. Notice, again, we give the oxidation number for the individual chlorine species, not the combined Cl2. The zinc has a +2 oxidation state, chloride -1, and the copper, again, because it's an element, is 0. So again, spectator ion in this case is my chloride ion. So I'm going to remove it when I write out the ionic equation. So I have my zinc, and I should do my state symbols, plus my Cu2+, which is my aqueous, going to zinc 2+, which is aqueous, and my copper, which is my solid. So in this case, it is the zinc that is being oxidized because its oxidation number is going up from 0 to +2. So this is my oxidation half equation. This is where I'm going to add in my electrons, because oxidation is loss of electrons. The electrons are coming loose. So I'm putting them on this side, and you've got 2e minus. Make sure it charge balances. So 2 plus 2 minus gives you 0 on this side and 0 on this side. And the copper, well, the copper is being reduced from the plus 2 to the 0. So it is gaining 2 electrons to make neutral elemental copper. And again, I'll put the state symbols in there. We need to be able to combine half equations and use them to do an overall redox ionic equation. Now, this is a little bit complicated, and there are steps that you need to go through. So I suggest you pause the video at this point and have a good read of those rules and how you use them to write half equations. And then we're going to move on and we're going to look at some examples. The examples are going to get progressively more complex as we move through. So hopefully you've had a chance to read through those how to write and use half equations. As I say, we're going to start with some easy ones and we're going to get progressively harder as we move through. So the first reaction is the reaction of chlorine with bromide ions to produce bromine and chloride. So the bromide is being oxidized to bromine. So the oxidation number of the bromide is -1 and the bromine is 0. So we're going from our bromide ion to our bromine molecule, and put a half in front of that, and an electron. Again, I could double this up and I could put in 2 in front of this one and 2 there. The chlorine, therefore, must have been reduced from chlorine to chloride. So chlorine, again, oxidation number 0, and chloride is -1. So again, we're going to do that equation. So you've got half a chlorine molecule, and it's gaining an electron because it's being reduced to become a chloride ion. Now what we have to do is we have to combine the two half equations to make a total equation. The important things to remember is that the electrons have to cancel. The electrons never appear in a total redox equation. They only appear in the half equation. And when we add the two half equations back together, the electrons must cancel. Well, they do in this case because I've got an electron on this side, an electron on this side, so I can just add the two half equations together. So I get Br negative plus half Cl2 going to Cl negative plus half Br2. Just go back and double check it by charge balancing it. So I've got a -1 charge on this side and a -1 charge on this side, so that charge balances. In the next example, we're going to react iron with chlorine to give iron 3 chloride. Well, the iron is obviously being oxidized because it's going from a 0 oxidation state in the element to the +3 oxidation state in the compound. So we have Fe going to Fe3+, and it's lost 3 electrons. Remember, it needs to charge balance. The chlorine, on the other hand, is going from chlorine, which is the 0, to the -1 of the chloride. So I've got chlorine gaining electrons to become the chloride ion. Now, in this case, we have a slight issue because these electrons do not balance. So we are going to need to times each equation up so that the electrons do balance and therefore do cancel. So I'm going to times the whole of this top equation by 2, 3 2's being 6, and I'm going to times the whole of this bottom equation by 3, 3 2's are also 6, so therefore the electrons would cancel. So I've got 2 Fe and 3 Cl2 going to 2 Fe3+ and 6 Cl-. So I can kind of rewrite this equation if I want to. This is perfectly fine, but it's more usual to write it as 2Fe plus 3Cl2 going to 2FeCl3 as a compound. But if I put state symbols on there, which I really should do, that's a gas. This is aqueous, and this is aqueous. So this is a solid, and this is a gas, and this would be aqueous, so it would split up into its ions anyway. So the next examples are a little bit more complicated because they involve oxo ions. So this is the oxidation reaction of iron 2 to iron 3 using manganate as an oxidizing agent. It's quite a popular equation. So the iron being oxidized from Fe2 plus to Fe3 plus, that is relatively straightforward because we're going to take the iron from the FeCl2, which is 2 plus, and we're going to oxidize it to the Fe3 plus. And we're going to get an electron coming loose. That one's relatively straightforward because we're just going from the plus 2 oxidation state there to the plus 3 oxidation state there. It's the manganese species which is a little bit more complex. So there are a couple of things that students are tempted to do when faced with an equation like this. The manganate species MnO4- turning into Mn2+. The first one is to split up this and just ignore the oxygens, and just to write something like Mn plus 7 going to Mn plus 2. And that being our oxidation number. Now that you cannot do. Do not do that. The reason you can't do that is this oxidation state, this plus 7 oxidation state, is very, very unstable. The only way you can actually get this oxidation state is by combining it with oxygen. So this has to stay together. You cannot split off the oxygen from it. So it has to stay as the MnO4-. Anything really plus 4 and above needs to be stabilised, usually with oxygen. The other temptation for this reaction is to go, well, I've got some oxygens here, so I'm going to put some oxygen over this side as well, and just put 2O2. Again, that is not allowed. The reason for that is in a half equation, only one species can be changing its oxidation number, and we're actually interested in the manganese in this case because the manganese is already changing its oxidation number. You cannot change oxygen's oxidation number as well, which you would do in this case because the oxygen we're going from -2 to 0. So again, that is not allowed. What we are allowed to do is we are allowed to add water and hydrogen ions, in other words acids, to the reaction in order to get the oxygens to balance. So we're going to start off with the MnO4-, and we're going to turn it into the Mn2+. So the first thing I need to do is to balance the atoms. Well, I have 4 oxygens on this side, so I'm allowed to make 4 waters on this side, because in this case the oxygen keeps its oxidation number of -2. I'm not changing it. I've got now 8 hydrogens on this side, so I'm going to add 8 hydrogen ions on this side to get it to balance. Again, I'm allowed to do that because I'm just adding acid, so this is acidified manganate. This is why we need to acidify the manganate, but again the hydrogen is not changing its oxidation numbers. Now, I need to work out the electrons. There are 2 ways to do this. I can either work out the oxidation number of the manganese here, which as we've worked out before is +7, and it's going to +2. So that's a change of 5. And it's a reduction equation, so it's 5 electrons, because the oxidation number is going down. The other way to do this is to charge balance it. So this side, the charge adds up to +2. So on this side, the charge must also add up to +2. Well, I have 8 hydrogens of +1 and 1 manganese, so that makes +7. So I need to take away 5 to get down to +2. Then it becomes straightforward again. I'm just going to balance out the electrons by timesing this top equation by 5. So I get 5 Fe2+, plus my MnO4 minus plus 8H positives going to my Mn2 plus my 4 waters and my 5 Fe3 plus. Notice again that the electrons need to cancel. Similar idea, we're going to use dichromate to oxidize iodide in an acidic solution to produce iodine and chromium 3 plus. So I'm going to actually start with the oxidation equation because that's slightly easier, because I'm going to turn my iodide into my iodine and I'm going to balance it, and I've got 2E minus. Now I'm going to do the reduction equation because that's slightly more difficult. So I'm going to start with the dichromate, Cr2O7 2 minus, and I'm going to turn that into Cr3 plus, and I need to balance it. So I've got 2 chromiums on this side, makes 2 chromiums on that side. I've got 7 oxygens to get rid of, so I'm going to make 7 waters. I can do that because I'm not changing oxygen's oxidation number, and to balance it I will need 14 H positives. Again, I could either use charge balancing or work out the oxidation numbers. In this case, I'm going to do charge balancing just to show the difference. So I've got a total charge on this side of +6 because I've got 2 3 plus ions. I've got 14 1 plus, that makes 14. And I've got these 2 minus here, so that makes +12. To get it down to +6, I need to add 6 electrons. The other way to do it is to work out the oxidation numbers. Well, the oxidation number of the chromium species here is +3, and the oxidation number of the chromium here, you've got 7 oxygens of -2. 2 minus is the total charge on the ion, so each chromium must be +6. So you're going from +6 to +3, that's a change of 3, but there are 2 chromiums, so that's a total of 6 electrons. Again, I need to balance it up and cancel the electrons, so I need to times this bottom reaction by 3, 3 2's being 6, so I have my chromium, or my dichromate, sorry, Cr2O7 2 minus plus 6I minus plus 14H positive going to 2Cr3 plus 7H2O plus 3 iodines. And again, just double check it by charge balancing. Last but not least, I've got manganate in an acidic solution oxidizing nitrate 3 to nitrate 5. So we're going to start this time with the reduction equation. MnO4 minus is one we've come across before, going to Mn2 plus. And again, I need to get rid of these oxygens, and I can do that by adding water. And I have 8 hydrogen ions on this side. Again, I can either charge balance it or I can work out the oxidation numbers, but either way, I get 5 electrons being gained. Now we're going to look at the oxidation half equation, so the nitrate 3 going to the nitrate 5 ion. So again, I have nitrate 3, which is NO2 minus, and this is going to the nitrate 5, which is the NO3 minus. Again, I've got to balance the oxygens. In this case, I'm going to put water on this side, H2O, to balance the oxygens, and then I get 2 hydrogen ions on this side. This is oxidation. Oxidation is loss. Again, I can either do this with charge balancing, or I can work out the oxidation numbers. Well, the nitrogen here is +3, and the nitrogen here is +5, so that makes +2E minus. Again, I need to combine them, and when I combine, I must remember to cancel the electrons. So I'm going to times this top equation by 2 and this bottom equation by 5. So writing it out, it's quite a long one, so you're going to need a little space. You have 2MnO4 minus plus 16H positives plus 5NO2 minus plus 5H2O's, and I'm going to cancel some of the waters and some of the hydrogen ions in a minute. Going to 2Mn2 plus 8H2O on this side plus 5, and I'm running out of room, NO3 minus plus 10H positives. Now I can do a little bit of cancelling. Well, I can cancel all but 6 of those hydrogen ions. With those hydrogen ions, I can cancel all of the waters with some of these to leave me behind with 3 waters, and I can rewrite it then as 2MnO4 minus plus 6 H positives plus 5 NO2 minus going to 2Mn2 plus 3 H2O plus 5 NO3 minus. And that is probably the most complicated one you're ever going to come across.